My name is Mohak Chadha. I'm a second year PhD student at the chair of Computer Architecture and Power Systems at the Technical University of Munich, and this is my Big Data 2021 presentation on the topic Fedless, Secure and Scalable Federated Learning Using Serverless Computing. Before talking about our contributions, I have to cover a bit of background first. The main problem with traditional distributed deep learning is that it usually requires all training data to be stored on a central server. This creates problems for using DNNs in privacy-sensitive domains like healthcare and banking. Moreover, the recent legislations on data protection and privacy, such as the European General Data Protection Regulation, makes it impossible to train DNNs on data stored and processed in different countries. But also, consumer products are affected. For example, the auto-completion feature of Google's keyboard on Android mobile phones uses distributed deep learning. Federated learning describes a new learning paradigm for data holders to collaboratively train an ML model while keeping their data private, meaning that the data never leaves their device. It tries to solve the fundamental privacy problems in distributed learning. FL can be broadly classified into cross-device and cross-silo. In cross-device, the clients are mostly mobile and edge devices with limited compute capabilities, while in cross-silo, the clients are organizations with sufficient compute capabilities. Federated learning, interestingly, has many similarities to distributed machine learning. And novel research in this area has found that serverless computing can be really useful in these settings. Some of the important features for us of serverless and fast in particular are: in fast, users execute stateless ephemeral small units of code called functions. Fast offers an image-driven design and offers a pay-per-use billing model. There's plenty of prior work on distributed ML using fast. However, it does not support federated learning and often only supports one cloud provider or specializes on HPC infrastructure. And they have several issues related to security. Naturally, we ask ourselves, could federated learning also profit from serverless technologies? We think indeed it does. Some of the key problems in FL are, most of the clients have heterogeneous hardware, which has a high barrier for entry if we require data holders to do this. Moreover, it often leads to over-provisioning and cumbersome infrastructure management. Since FL traditionally follows a synchronous process, it turns out that clients that finish with their training often spend lots of time for others to finish until a new round begins, which leads to unnecessary cost or wastage of resources. Scalability. At the end of each FL round, lots of clients report back their results at the same time suddenly. Function as a service fundamentally tries to solve many of these problems. It allows for rapid scalability during request bursts and automatic scaling to zero when resources are unused. It follows an attractive pricing and development model, and finally provides ease of use. So what is still missing with serverless FL? So simply switching from a stateful FL system and using serverless functions is not a good idea. Because of critical limitations of serverless functions, for example, the maximum amount of runtime or the memory that a function can have, and no local persistent storage due to the stateless nature of fast functions. Moreover, everything has to be provider agnostic. Data holders operate their own clients. Forcing them, for example, to use AWS might not be possible for a hospital if they are not legally allowed to upload their data to the cloud. Issues with authentication and authorization. The access to the parameter server has to be secured. And typical communication protocols in current FL system, for example gRPC, cannot be used with serverless functions. And there are several other issues. So in this work we present Fedless. So Fedless is a system and framework for federated learning on heterogeneous fabric of fast platforms. which means that it can simultaneously work across clients in the cloud, edge devices, or on on-premise data centers. It provides essential features for security and supports training of clients using differential privacy. It has a modular design and is easily extendable. It supports 6 fast platforms out of the box and offers various performance optimizations to fix the shortcomings of serverless functions. The system architecture of Fedless can be grouped into several components. Clients are essentially serverless functions which get their data from an S3 bucket or a mounted network drive. The controller is a stateful process which manages and monitors the entire training cycle. The parameter server is MongoDB. We chose it because of its reliability, replication support, and creation of RBAC rules. The aggregator implements the FL strategy, in this case the federated averaging algorithm, which updates the model weights. It also is responsible for computing the accuracy of the trained model. The security features of Fedless can be divided into 4 aspects: function ownership, authentication and authorization, parameter server access, and general security features. In Fedless, data holders are responsible for their functions. So this allows for full control and flexibility. All participants and requests are authenticated. Only the trusted FL server can invoke functions. Only identified and approved functions can join the fabric. And also we have support for custom identity providers such as OAuth2 and SAML 2.0. So the mechanism used for authentication and authorization must be agnostic to the cloud or the fast platform used and should require no manual intervention. For this, we make use of AWS Cognito, which is based on JSON Web Tokens. We follow best practices for security and counter most of the vulnerabilities listed by the Open Web Application System project with a system design. For example, the isolation of authentication and authorization by using separate functions. The privacy problem in a FL is that the model parameters can leak information about the training data. So there are 2 types of attacks: membership inference attack or model inversion attacks. And there are different ways to prevent this. For example, encrypting the parameters using different techniques such as SMC or HE, using differential privacy. And most of the times a hybrid approach between these 2 is used. So encryption is problematic for FAST because of huge computational overhead and complex inter-function communication. So DP is better suited for FAST, and clients can add noise to the parameters before they upload to the parameter server. And also, since the data holders have complete control of their functions. So Fedless essentially implements local differential privacy, which is a type of record level privacy in which the client functions add Gaussian noise to their parameters before uploading them to the parameter server. So the technologies used in Fedless are, it is based on Python 3 and supports TensorFlow 2 and Keras, with support for custom data types and models using the Pydantic library. The different performance optimization that we did include a streaming aggregation. So we implemented a running average model aggregation method so that the aggregator does not have to load all the model updates in memory at a single point. We implemented an LRU cache for the global namespace due to the ephemeral stateless nature of fast functions, and also implemented federated evaluation, details about which can be found in the paper. So how does a training round with Fedless work? So at the beginning, the FL admin configures and starts the training process. The Fedless controller requests a new invocation token from the authentication server using the credentials configured by the FL admin. Then it invokes the randomly selected FL clients during the round using the controller. The clients validate the token to ensure that the invocation is valid. The clients then use the supplied parameter server credentials to load the latest global model. The clients use their local datasets to perform the local training, optionally using local differential privacy. All clients upload their updated parameters. After all clients have finished training, the controller invokes the aggregator function, which aggregates the weights. The aggregator function updates the global model. The controller then starts the evaluation for determining the accuracy of the updated model. So the training process continues until a desired tested accuracy is reached. Moving on to our experiments. So we tried Fedless with different data sets and different models, but most important findings can be shown with two data sets, MNIST and CNN. MNIST, which is an image classification task with small CoVNet, and FMNIST, which is an extended version on MNIST with 10 times a larger model. So we deployed the clients across 5 different fast platforms. So on increasing the number of clients with the MNIST model, we see that stragglers are the main factor which contribute to the round duration, and there is no significant effect on the client runtime, but only the aggregator function slows down slightly. So this essentially means that Fedless scales easily for small models. On the other hand, if you look at FMNIST, so here we see that on increasing the number of clients, the aggregation time significantly increases. So on investigating this issue, we found that it is not really related to networking or compute power, but on the ability of a parameter server to handle multiple clients uploading large models simultaneously. And we are currently replacing our parameter server so that our system is more scalable for larger models. So, but we were also especially interested in how our approach compares to traditional non-serverless FL. So we deployed 100 clients on same hardware with same CPU capability requirements. One time with the traditional FL framework FLAR using Docker plus C groups, and other time with OpenFast. So we find that the fast-paced approach is slower, some overhead likely stemming due to the fast platform, and loss due to the pure nature of functions, for example, cold starts and no persistent storage, and also some due to the parameter server communication. So we report all cost values with respect to Google Cloud, and we don't calculate point estimates but calculate broader bounds. For this, in our calculations, we include how costs would change if the Fedless clients were 2 times or 3 times slower, and FLAR clients were only 0.5 times slower. So for all our results, we see that the fast-paced approach is cheaper as compared to the IaaS-based approach. However, the more clients we use, the difference decreases. So this is intuitive because the better the resource utilization in VMs, the more cost efficient they are compared to serverless. However, we think that these results are very promising since in FL there can be millions of devices with only a few hundred active in each round. So to conclude, so serverless FL with security and differential privacy is possible across a fabric of heterogeneous fast providers. Fedless can scale to hundreds of clients for small models, not currently with large models. We already know a reason for this. And so the current limitations of our approach are, so different fast platforms have quotas for fast functions, for example, the amount of memory they can be allocated and specific amount of runtime. And multi-cloud makes it harder to have a common system. Compared with traditional IaaS, we found that Fedless is slightly slower, but it can be cheaper and more resource efficient. In the future, we are working with different fast platforms with support for functions that can share GPUs. We are working on improvement on our system design, moving towards a completely event-driven system rather than a current hybrid approach. and working on strategies for mitigation of stragglers in serverless FL, and also strategies which account for heterogeneity among clients. Thank you.